Hopefully so far you've seen that the related rates examples that we've been through in class and on the videos have depended on your expertise in geometry class, or at least to remember formulas for area and volume. A lot of times there are related rates examples that use similar triangles, and I'm going to go over a couple of the typical examples with you. And the first one, the very typical one, is this, and I'll give you a minute to write this down. But there is a 6-foot man who's walking away from a 20-foot tall streetlight. So just imagine that for a minute. And he's walking away at a rate of 4 feet per second. How fast is the length of his shadow changing? So you can imagine the shadow. How fast is the length of this shadow changing when he is 30 feet away from the light? So our first problem is to draw a good picture of this example. So what we have is, let's see, we have a 20-foot tall streetlight. So I'll draw this over here. Streetlight should be just a plain old vertical line here. You want to put a little light on the top of this, you can. And this length, this height, is 20 feet. All right, so the man is walking away from this street light. So this man is 6 feet tall. So here's the man. And he's walking on the ground. We can put a little head on him. Anyways, he is 6 feet tall. And here's the ground. And he's walking away from the light post, so he's walking in this direction here. And this light shines down on the man and creates a shadow on the ground like this. So here's the man. Now this height of the man is a constant in this equation, and this height of the light is also a constant in this equation. So what we want to try to figure out is what are the variables, what things are changing, and what's the rate that's given, and what is the rate that's asked for. So what we have is, let's see, it's telling us that this man is walking away from the light at 4 feet per second. So we have a distance here from the man to the light, and this is changing because he's walking in this direction. And you can call this anything you want. I think I'm going to call this distance m for man, or you can call it x if you want, but we actually have two x variables here. So I'll just call this m for man. And we don't know what this distance is going to be 30 feet after we get done taking the derivative of whatever it is that we come up with a formula for. So we'll be plugging in that later. So what we're given here is that dm dt is equal to 4 feet per second. And we're asked for how fast is the length of his shadow. Well, this right here is the shadow. So we can call this anything we want. I guess I'll call it, I hate to call it S because S's look like 5s. But let's see, I guess I'll call it H for shadow. And it asks us how fast is the length of the shadow. So H is the length, and how fast is it changing? So what we want is a dH dt. How fast is that changing? Now what we want to do is we want to figure out how the H variable and the M variable are related to each other so that we can take a derivative and so that we can plug in what we're given and what we want. So we're given the m value is 30. After we take the derivative, we'll plug those values in. So how are H and M related to each other? Well, I already told you that this is a similar triangles question. So this big triangle here and this little triangle here are similar triangles because the angles are all the same. This angle and this angle are equal to each other, and these share the angle, and these are both 90 degrees. So this triangle and this big triangle, being similar triangles, have sides that are proportion with each other. So if you remember the proportion, there are different ways you can set up this proportion, but you can say that this height and this base divided by this height divided by this base is equal to this height divided by this base. So we'll say, using similar triangles, taking you back to geometry class, we have 20 over this whole base, which is h plus m, is equal to this height, 6 feet, divided by just plain old h. And now what we have is a formula that relates our two variables, the h and the m. And so we can take derivatives and plug in our given values. But I don't think I want to take a derivative looking like this. I think we can make a new equation out of this to make it real easy to take a derivative. I'm just going to cross multiply here, which tells us that 20h is equal to 6h plus 6m. And then when you subtract 6h from each side, you get 14h is equal to 6m. And right now, if we wanted to take the derivative, this is pretty easy, and we can start plugging in numbers. So the derivative of 14h is just 14 dh dt, and the derivative of 6m is just 6 dm dt. And we want dh dt, so that'll be our variable. And we're given dm dt, and it looks like it really doesn't matter that the m value is 30 feet. We'll just plug in dh dt is equal to 6 over 14 times dm dt, which is 4. And reducing that down to 2 over 7, it looks like our rate is 12 over 7, and this is the change in the shadow. So this would be feet per second. So once we get down to taking derivatives, it's pretty easy. I think the hard part is just drawing the right diagram and setting up the equations to relate the variables with each other. That'll be the hardest part for you when you attack these related rates questions. And here's a little twist to this problem. Now I want to know how fast is the tip of his shadow moving. So this is like a part B to this question if this is part A up here. So part B says, how fast is the tip of his shadow moving? At this point in time. So you can imagine if you've ever been walking away from the light pole, if you're walking at a steady rate, this shadow here will be getting, let's see, if you walk further and further and further away, this shadow will be getting longer and longer and longer and longer. So this shadow is really moving at a rate much faster than what, at some point in time, than what you're walking along. So we'll find out how fast that tip of the shadow is moving. Well, it's the same diagram, but the variables are related in a similar way. Let's see, we'll put this as 20, and this is 6, and we'll call this m, and because we have dm dt being the same value of 4. But now what we want to know is we want to know how fast this entire this entire base of this triangle is changing over time. So we'll call this x, this entire base. And what we want is dx dt, because we want to know how fast this whole thing is moving away. So we want dx dt this time. And everything else that we've been given before is the same. And even how you set up the similar triangles is going to be the same. 20 over this whole base is equal to 6 over this base, but we're not calling this h anymore. 20 over x using similar triangles is equal to 6 over, well, what's the length of this? Well, the length of this is this whole length, x, minus m. And so now we have our x variable and our m variable set up so that they're related to each other. And we can just proceed just like we did on the last question. So we have 20x minus 20m is equal to 6x. And just doing a little bit of algebra, we have 14x equals 20m. And so now we're going to take a derivative of this implicitly with respect to t. And what we have is 14 dx dt, and that's what we want, is equal to 20 dm dt. And we know that dm dt is equal to 4 feet per second. So we can just substitute a 4 feet per second here, and we can divide this by 14. And now the rate of change of this this whole length here is, this is 2 over 7, so this looks like it's 40 over 7. Hopefully I did my math right. And what are the units? It looks like it's still feet per second. So we got 40 over 7 feet per second. That is the rate, that is the tip of the shadow is actually changing. It doesn't really have a whole lot to do with the length of the shadow. Remember the one before was how fast is the length of this shadow moving. The other, this little twist is how fast is the rate moving away from the light. So just be careful on what you're being asked for. The last example I'm going to do today is an example that has to do with a cone-shaped object. Some of the examples that we'll be doing really soon, maybe in class tomorrow or maybe on tomorrow night's video, is going to be a combination of a cone-shaped object and some triangles, some similar triangle questions, a combination of the two. So let's get used to a cone question along with a similar triangles question. This one does not have a similar triangle situation in it, though. So this is how it goes. The radius and the height of a cone are both increasing at a rate of a ½ centimeter per second. What's the rate of the volume? At what rate is the volume changing when the height is 9 centimeters, that's the height of the cone, and the radius is 6 centimeters? So you can take a moment to jot all this down. But what we have is we have a radius, we have a height, and they're both increasing at rates that are equal to each other, but they both have a dr dt and a dh dt. That's the rate. Whenever you see the word rate, you know that's a change in the variable over time. And now what we want is what is the rate of the volume. So we have to have an equation that relates volume to radius and height. And the volume of a cone, you should start to memorize these formulas. The volume of a cone is 1/3 times pi r squared times h. And so I think we've taken care of all of the variables in this particular problem. We've got volume, we've got radius, and we've got height. And so now what we need to do is, well, we should probably draw a picture of a cone. And there's the radius of a cone, r, and the height is h. And what's happening to this is that this radius is expanding, and so is the height. The height didn't have to expand as the radius expanded. It could have just been the radius expanding, or it could have just been the height expanding. But in this particular problem, both the radius and the height are expanding. And they really didn't have to be expanding at the same rate either, but they do in this problem. So we're going to take the derivative once we've got this equation that relates the variables that are in this problem. dv dt is equal to, remember, 1/3 pi is a variable. So I'm going to pull the 1/3 pi out in front. And now r is changing, h is changing. Those are both variables, and it's a product of two variables. So we have to use the product rule on this. First times the derivative of the second, plus second times the derivative of the first, which is 2r dr dt. And now what we want is dv dt and I think everything else is given to us. They give us the height is 9, the radius is 6, they give us the change in radius over time, which is dr dt. It's changing at 1/2 centimeters per second, and all these are in centimeters. And they're giving us the change in height, which is dh dt, which just happens to be the same as the rate of the radius changing, 1/2 centimeter per second. So now all it is a matter of plugging those numbers into this formula, and we can find out what we want. So dv dt is equal to 1/3 times pi. Let's see, r squared is 36, dh dt is 1/2, plus h is 9, 9 times 2 is 18, and 18 times 6, I don't know, it is 108. 108, and dr dt is 1/2. So what do we have here? We have 1/3 times, this is 18, and 1/2 of 108 is 54, and 1/3 of 18, 1/3 of 18 is 6. Okay, so we have 24 pi is our final answer. And what is this? The rate of the volume. So the volume will be in cubic centimeters per second. And that will be the final answer. That's the rate of the volume changing. I think that's what they want. What is the rate of the volume changing? Yep. So there's your little cone question. And that's it for today.